Hi, my name is Jason Mote, and I'm a junior at UAH in the Department of Chemical Engineering. This summer I worked with Dr. Baird from the Department of Chemistry to research chemical reactions at the critical point of solution. A critical point is an intersection between two or more properties of a system that cause phases to coexist. An example of this is shown in the diagram on the right. Our two phases were isobutyric acid and water. Usually they are separate, like oil and water, shown in the left diagram. When heated above their critical temperature at a certain composition, they merge into one phase, as shown in the picture on the right. There are two kinds of variables we can measure in a critical system, and those are field and density variables. A field variable is constant in all phases. An example of this is temperature. A density variable is not constant in all phases. An example of this would be the concentration of isobutyric acid. In the left diagram, the concentration is not the same in both phases. A critical fact is a trend where the derivative of a density variable with respect to a field diverges to positive or negative infinity. Critical effects are present in mixtures where the Gibbs phase rule is equal to 3. Our experiment measured the solubility of barium sulfate, which is a density variable, with respect to temperature, which is a field variable. This was done by making a 150 milliliter sample of isobutyric acid and water at 38.8 mass percent isobutyric acid. We use the analytical balance pictured at the right to make this sample. Solid barium sulfate was added to the test tube along with a stir bar, and then they were put in the water bath, and the local critical temperature was found. The water bath is pictured at the right. The test tube was stirred for 24 hours, and then it was settled for 24 hours to allow suspended barium sulfate to fall back to the bottom of the test tube. And then 3 5 milliliter samples were taken from the test tube. The temperature and mass were recorded. Steps 4 through 6 were repeated until we get to about 10 samples. Then we take the samples up to Western Kentucky University so we can get the solubility with inductively coupled plasma mass spectroscopy. Last two steps of the procedure were labeled as ongoing because COVID-19 prevention protocol interrupted our experiments. And we're going to plan on taking the rest of the samples and getting them analyzed during the fall semester. The main application of critical phenomena that our group is investigating is a process that captures carbon dioxide from the atmosphere. It uses the enhanced solubility of supercritical mixtures to do this. Flowchart is shown here. So CO2-rich air is input into the absorber, and excess air is purged through the bottom. And there is a supercritical mixture of isobutyric acid and water inside the absorber. Because of its high solubility, it can absorb some of the CO2. It's then sent to the desorber, where the temperature is reduced and the solubility is reduced also. This releases the CO2 and it is removed from the system via a purge stream. The isobutyric acid is recycled back to the absorber. This is what gives this system an advantage over current systems. The solvent doesn't need to be regenerated or resynthesized, so by recycling it, money is saved. Future research includes testing the solubility of multiple solids at once, so we have one with barium sulfate and calcium sulfate in the same system. These are F=4 systems, so we don't expect there to be a critical effect. We also plan to repeat the solubility test with a base and water mixture instead of an acid and water mixture. We have triethylamine in water and 2,6-lutein in water planned. That's about it for my project. Thank you for watching and have a good day.